I want to remind you of a couple things because these are very important facts when writing formulas and names. So we actually have a trick to figure out our valence electrons. And to remind you what valence electrons are, they are the outer shell electrons. So when you draw an atom, we draw the Bohr diagrams, which we learned last week, the outer shell. Those electrons are called valence, and there is either the option of 1 up to 8 valence. We never have more than 8 valence. And our trick for valence is everything in this first group. Remember, groups are vertical, have 1 valence. Group 2 has 2 valence. Group 13 has 3, 4, 5, 6, 7, 8 valence. Okay? The only hiccup in there being helium, it only has 2 valence, although we won't really use that one a ton. Okay, so for example, if we were trying to figure out arsenic's valence, we would see that it was in group 15 and it would have 5 valence electrons. So it's a nice little tip to quickly look at the number of outer shell electrons. Now, the octet rule is the rule that dictates bonding. So an octet rule means that every atom wants 8 valence electrons. Okay, so 8 valence electrons, it means that it has a full valence shell. So the reason for ionic and covalent bonding is to fulfill that octet rule. So keep that in mind as we learn different components in this chapter. So there's 2 ways of naming. We're going to look at the IUPAC way, which stands for International Union of Pure and Applied Chemistry. Therefore, we are going to use Roman numerals here. We're going to use the IDE ending. And then, of course, you are familiar with common naming. So, for example, if you've heard of lime or lye or vinegar, those are all examples of common naming. We're not going to work on that in this class. We're going to look at the systematic naming or IUPAC naming. Now, we talked about valence electrons a few slides ago, but now we want to discuss how does charge come into play. So we want to keep this in mind. If we want 8 valence electrons, okay, we have to keep in mind that atoms are going to gain electrons to get to 8, or they're going to lose electrons to get to 8. Okay, so 8 is the number that we want to reach. So remember I told you that group 1 has all 1 valence. So you have to keep in mind, is it easier to lose or less energy to lose 1 valence electron or to gain 7? So when I say it loses 1, it actually goes to a previous shell, and that lower shell is filled with up to 8 valence, which it would have 8. So it is easier, less energy, to lose 1 valence electron if you're in group 1. That means that you have 1 more proton than electron, which gives it this +1 charge. So anything lithium, sodium, potassium, rubidium has a +1 charge when it becomes an ion. And remember, ions means that you are gaining or losing electrons. So the +1 means you have 1 more proton than electrons. So you're actually losing an electron when you see a +1 charge. Same thing with group 2. Group 2, as we've learned, has 2 valence electrons. Is it less energy to gain 6 or lose 2? It is easier to lose 2 to then go to a lower shell to reach that octet. So therefore, we're going to lose 2 electrons, which gives us this +2 charge when it becomes an ion. Now, we're going to skip this center section until we get a little bit more into this, but we're going to talk about the nonmetal section here. So anything in group 13, it is easier to lose 3 electrons than it is to gain 5 to get that octet. And then we're also going to talk about group 14, which is carbon. You can see carbon there. And we want to talk about this one. Not only will it lose 4, but it can also gain 4. So this actually is a ±4, but to be fully honest, it doesn't really create ionic bonds. So we're not going to really focus much on group 14 right now. Now, anything in group 15 has 5 valence, and again, the less energy option is to gain 3 electrons to get to 8. So therefore, anything in group 15 has a -3 charge. Anything in the oxygen or group 16 has a -2. It's better to gain 2 electrons than to lose all 6 of them. And then anything in what we call the halogen group has a -1 charge. Now you're going to ask, why does this last group, we call this the noble gas group, not have any? Remember, all of these in the noble gases have already 8 valence electrons, so they are already fulfilled. Therefore, they're not going to bond. The main reason for ionic bonding is to reach an octet in both atoms. Okay? So you're going to use these charges a lot. Now, when I told you that atoms can gain or lose, metals, which we know metals are more on this side of the periodic table, the left, okay, so this middle section and this left-hand side, those are metals, and what they do is they actually always are going to lose their electrons because they only have 1 or 2 or 3. So it's easier to lose that than to gain to get to the octet. When they lose electrons, they become a cation. And a cation has a positive charge. And remember, that is because there are more protons are positive, and less electrons. And we know that electrons are negative. So more protons means positive charge. Now here's a very dumb way to remember cations. I think I showed you this last chapter. Cations, if you draw a little cat head, you can make it a plus sign for the little nose. And this is a very common way of remembering cations are positive. And a positive charge means losing electrons. When we have a cation, the name doesn't really change. So potassium is in group 1. You can see that right here. So potassium is always going to lose 1 electron, and this becomes a K plus 1. Okay, so that charge, as I showed you up here, is what that atom becomes, and we just call that a potassium ion. So I want to reinforce the potassium K versus K ion are two different things, okay? Same number of protons, different number of electrons, okay? Magnesium is in group 2, and group 2 things always have a plus 2 charge, meaning they have 2 electrons being taken away from them. We just call that the magnesium ion. So metals do not really change their name. We're going to see nonmetals do, but metals do not. All right, the last one here is aluminum. We know aluminum is in group 13. It usually has a plus 3 charge, and we're just going to call that the aluminum ion. All right, now, nonmetals is where the name actually changes. So nonmetals are closer to an octet, so they are going to gain electrons, and we call them anions when they gain electrons. Anions have a negative charge to them. Okay, and again, that is because there are more electrons than protons. So overall, that charge comes from an unequal distribution of negative to positive. So when you have a negative charge overall, okay, you have more electrons than protons in the atom. So fluorine, let's find fluorine on our chart here, and we're going to look at fluorine and chlorine while we're up there. So fluorine and chlorine are right here, and they're both in the -1 column. So they are going to, when that -1 means they're going to gain 1 electron, they become F minus 1 and Cl minus 1. Okay? Now, when we name anions or nonmetals, you actually change the ending of the word to IDE. So instead of it being fluorine, it is fluoride when it's an F minus 1. F by itself is fluorine, F minus 1 is fluoride. Same thing with this one. This is chloride, okay? Meaning use the charge of the ion on the periodic table. So we're going to look at oxygen and nitrogen now. So I'm going to go ahead and back up. Oxygen is -2, nitrogen is -3. So you're going to have to remember those charges. They will not be given to you, and you're going to utilize those a lot. Oh, excuse me. I don't want to do a negative sign there. They gain 2 electrons. They gain 3 electrons to reach that octet. So that becomes O minus 2 and N minus 3, and we call that oxide. When it has that charge, we call this nitride. So this ending is very important to understand. Cations do not really change the ending, and anions do change the ending. All right, now we are going to learn how to write our first formula for an ionic compound. Remember, an ionic is a metal and a nonmetal coming together. We're going to see here an example. What you do is, once you figure out these charges, you crisscross them and bring them down to the opposite corner to create your formula. And this works really well, and it's pretty easy to understand. So what I'm going to need you to do is, with your periodic table around, or with the one in the previous slides, make sure you check out the charges. Na is in group 1, so Na has a +1 charge, and I like to write that above it, so when I crisscross it, I can kind of see where it's coming from. Chlorine is in group 17. It has a -1 charge. To do this, you're going to bring these numbers down, and you do not bring down the plus and the minus. Those disappear. So this is Na1Cl1. You do not have to write ones in chemistry. You can, but you don't have to. So this is just NaCl. Okay, so when Na and Cl join, the formula is Na and Cl, or Na1Cl1. When you find magnesium, it's a group 2. and you want to make sure you're writing these negative and positive. Positive always comes first, which is the metal. Non-metal always comes second. -1 charge, group 17, crisscross them, Mg. Again, you can write that one or you don't have to write that one. So I'm just showing you what that looks like. I'm going to erase that and make that just MgCl2. Okay? Now we have Mg group 2. We have oxygen -2. Bring those down. You can write this as Mg2O2, but you're going to start to learn that when they're a number that can be simplified, you can simplify it. And it could be Mg1O1 or just MgO is more commonly the way we see it written. So K, group 1, S-2. Again, you're going to have to memorize these charges. So this becomes a K2S. And here we go. We have a +2 and a -3. And again, you'll get better at this. Mg3N2. So bring these down and make sure you are not putting in the positive and negative signs, okay, when you bring them down. So these are your first ionic formula writing. Now we're going to get into something a little bit harder here. These are polyatomic ions. You will be given this list. Well, you actually have this. You will be given this on tests. So you do not have to memorize this. You do have to memorize the charges we were just utilizing, but this whole thing is on your lecture packet, and you will be given this exact same list, okay? So I just want to point out a couple of things here. We have a bunch of cations, which are positive charges, so you can see these. And then most of these are actually anions, as you can see, meaning they have negative charges, so you're going to be using their name and their formula. All right, so make sure you are familiar with those as you go through them. So we're going to continue to come back to here. So if I were you, I'd make sure I had my lecture packet out and I was looking over the polyatomic ion list. So you do the same thing here. You crisscross your charges and bring them down, okay? But if there is something that has a number associated with it, you have to put parentheses around it because this number coming down belongs to everything. So you cannot write it like this. It is not SO43. It is 3 sets of SO4. So that is a little bit of something new we're going to have to look at when we work through these. Okay? Let's do some examples here. So we're going to go ahead and crisscross, and again, these are provided for you. You can find this on your polyatomic list. So you do that same thing, you crisscross, so Na, and again, that NO3 with a negative is a 1. You don't have to write that, but I'm just showing you, and this Na with a plus is a 1 as well. If you're going to show the 1, you have to do parentheses. Typically, we do not, so NaNO3 is your formula. Now, if it helps you, you can even circle and bring them down. So this is a 2 and a 2. They would technically cancel out, but I'm going to go ahead and show you what they'd look like if they didn't. SR2, HPO4. Now you have to ask yourself, bringing this 2 down, do we have 42 oxygens? The answer is always no. So if you're bringing a number down and there's already a subscript, then you put parentheses. Now, since these are both 2s, you can cancel them out, so it becomes SRHPO4. You cannot cancel out a number if it is associated with what we call a polyatomic ion. Okay, you can only cancel things out or reduce them if they are charges that you bring down. So let's go ahead and do this one. Again, you can crisscross and bring these down to help you, and that's going to be Fe2. And then CO3, again, do we have 33 oxygens? No, we have 3 sets of CO3. So go ahead and pause the video and finish up these examples and check your answers here. I do want to talk about this one. Because this is a 2 and a 4, you can reduce these. You cannot reduce this. You can only reduce the charges up above. So this can actually be written as this, or you can reduce this, just divide them, and it becomes PB1, which we don't write, CrO4, and then we can actually just make this 4 a 2 because we divided both sides by 2. Okay, so either one of those are options. Now we're going to learn how to name simple ionic compounds. We just learned how to write the formulas. Now we're going to learn how to name them, which is a little bit more difficult. So you're going to want to make sure you understand that your metal always comes first, which is on the left side of the periodic table. Your non-metal, it comes second. It is on the right side of the periodic table. And we need to realize that we change the ending of the second thing, or the anion, to IDE, like I showed you a couple slides ago. So when we name these, we're going to name the metal. This is sodium. And then we name the second thing, which is chlorine, but since it's an ion, because it's joining together with something else, we change the ending to chloride. Okay? So the first thing doesn't change, the second ending does change, sodium chloride. So let's go ahead and do this one. Li is lithium. Writing a little too big here, I'm going to write it below. And then fluorine is joining with lithium, so it's an ion, so it is fluoride. All right, then we have K. But remember, where does this 2 come from? You kind of have to visualize this. Where did it come from the beginning? So you have to remember that when K2O comes together, it was at first K plus 1 and O minus 2. Where did we get these numbers? We got them from that periodic table where we learned the charges. So when you see that 2, you just have to know that came from the O when it crisscrossed and came down. So you kind of ignore it for now, although we will not be ignoring it for very long. So potassium oxide. And then we have magnesium nitride. Okay, so you have to change this ending, IDE at the end. Again, where did these numbers come from? You can kind of crisscross them back up. That is, and the first sign is always a plus, the second is always a negative. Okay, so that is naming simple ionic, meaning there's only 2 elements, a metal and a non-metal. Now it gets a little bit more difficult when we're talking about polyatomic ions, and I pulled over this polyatomic list for you guys so that we could reference it as we go through here. So what you need to do is you need to visualize the 2 components of this formula. And when I say that, I mean the metal, which is first, and then the second half, which is what we're going to call the polyatomic. And I'm going to go ahead and underline that. So that is the second component. And then we're going to work on where these charges come from. So the K is simple. Okay, K is potassium. Nothing changes with the metal. You always name it the name that it is. Now, you need to find something on your polyatomic list that has a CO3. So if I do a quick scan, I can see right here, carbonate is a CO3 with a -2 charge. So we want to look over here and you say, oh, hey, there is a 2. Okay, so this 2 probably came from carbonate. So it's as simple as just writing the name carbonate. Okay, let's do this again. So we see magnesium, and we see an NO3. So I'm going to go ahead and look through here. Oh, I see an NO3. Please don't get it confused with NO2. It has to match the identical formula. So the other word for this is nitrate. So this is why it's so important to have that polyatomic list close to you. So this is SR, that is strontium. I'm trying to find something with an SO4. And if you look here, we have SO4 and SO3, so we're going to look at SO4. Now you're going to say, where is that -2 charge? I need you to keep in mind that strontium is always in group 2. It has a +2 charge. And SO4, as we just learned, is a -2 charge. So these cancel out. So you need to be able to see that these are canceling each other out. So this is called strontium sulfate. So I'm going to go ahead and name these ones. Sodium, and you're going to go ahead and look at your list and find something that matches ClO4. Okay, you're going to see that right here, perchlorate. You do not have to change the endings of any of these right now, okay? You had to change them in the previous examples, but in here you just take that exact word. You do not need to change it. Although a lot of these are ending in 8, they do not always end in 8. You just read the word and write it on there. All right, now NH4 is a little bit harder to see, but NH4 is one of the few cations or things in the beginning that is its own component. So instead of a metal, we're just going to write ammonium. And if you look again, this is in the NO3. It's the same NO3 as up here. That is called nitrate. And we see a Ca and a CO3, so that is calcium. If you look on your list, we also already used a CO3. That is carbonate. Okay? So this is not too bad. You do need to have your polyatomic list to be able to do this, but this does get a little bit more difficult. This is actually the most difficult it gets, and this is the center section. We call this the transition metals. So transition metals are right along here, group 3 through group 12, and there's a couple extras down here, and these have what we call fluctuating charges. Fluctuating meaning they change. So we have learned thus far, group 1 is always +1, group 2 is always +2. Typically group 3, especially right here and right here, is +3. Then we have a plus or -4. Then we have a, excuse me for that, -3, -2, -1, and this we don't really form ionic bonds. The ones I have in red never change, but the ones in the center do. Okay? So what we have to do is use Roman numerals to indicate the charge. So I want to do a quick Roman numeral review with you. 1 is just an I, 2 is I, 3 is I, 4 is IV, and you must know these. You're not given these values. So when you're writing these, you want to make sure that you understand the V is 5, and then we have VI for 6, VII for 7, VIII for 8, VI for 9, and then actually 10 is an X, okay? So when we're looking at this, we're talking about how the charge, instead of it being assigned, is actually given as Roman numerals. So when you see an iron with a 2, you have to know that means it's an Fe plus 2. Or a copper with a 1 is a Cu plus 1. So it's kind of a nice way to understand the charges. So for our last example here, we need to understand how to figure out the charges. So if you see the first element is not part of group 1 or group 2 or any of these red ones I showed you, then the charge changes. And the name requires a Roman numeral, okay? Roman numeral. So when we're looking at this, we need to uncrisscross. So what you're going to have to do is, one of them you're going to know. In this case, you're always going to know the anion, the second thing. So chlorine, I believe, belongs right here. Chlorine is a -1 charge. So this 2 had to come from the Cu. So therefore, when you're naming this, you write the element name, you write the charge, which it has to be a 2 to bring that down, and then you write chloride, okay, with the IDE ending. Let's do that again. Now, if you see these numbers coming down, especially next to parentheses, you can assume that's the charge. You'd also find sulfate on your polyatomic list, and it tells you it's SO4 -2, so that 2 is accounted for. That 3 had to come from the iron, so that is iron 3 sulfate. Okay, so you have to have your polyatomic list here, because these Roman numeral metals can be not only with polyatomics, but also with periodic table binary charges. So again, you're going to want to look at nitrate, that is NO3. You have to remember this 3 belongs with this. If your polyatomic list tells you NO3, the 3 did not come from this first thing. It came from the polyatomic. So actually this 4 came from the SN. That's an example of tin. Tin is SN, and that is a 4 nitrate. Now this is a little bit of a difficult one here. This is about as hard as it gets. This is Ti. You're going to have to know that O is always a -2 charge. And if you do not see a -2 charge coming down, then it had to be something that would cancel it out to leave a 2 left. So this could maybe be a bonus question. This would be titanium 4 oxide. And again, that's because if you had a Ti with a +4 and an O with a -2, when you crisscross these, they would cancel each other out so that you only had a 2 left here. Sometimes it takes a little bit of time to work through that one. Now, last thing here to finish up ionic naming, there are three transition metals that do not require Roman numerals. Do not, and you will have to memorize these. The good thing is if you use your polyatomic list, I actually provided them for you right here, and you will have this. So you don't need to put for AG, CD, or ZN a Roman numeral. It is assumed it is a +1, +2, +2. Okay? So if you see those, please utilize that list. So that completes ionic naming. you can go ahead and watch the next video for molecular or covalent naming, and I promise that is a lot simpler.